January 5, 1943, Kula Gulf, Solomon Islands. Lieutenant Red Cochran gripped the fire control director aboard the cruiser USS Helena as 4 D-3A dive bombers completed their attack run against the American task force. These Vals struck the New Zealand cruiser Achilles and were turning away with characteristic Japanese precision. Cochran armed shells containing technology that would rewrite the mathematics of aerial warfare. 2 salvos thundered from Helena's aft 5-inch battery. One of the departing Japanese aircraft erupted in flames without being touched, ripped apart by shrapnel from a shell that exploded 30 feet away. The pilot never understood what killed him. Neither did his commanders. Neither would the Japanese High Command for the remainder of the war. This was the first combat kill by a weapon that military historians would later rank alongside radar and the atomic bomb in strategic importance. The proximity fuse, deceptively codenamed the Variable Time or VT fuse, had just announced itself to the Pacific War. Over the next 2.5 years, if you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. This technology would fundamentally alter Japanese tactical calculations, shatter their aerial offensive capability, and save thousands of American lives. The transformation began not with brilliance, but with a fundamental problem that had plagued anti-aircraft gunners since aircraft first became weapons of war. December 7, 1941, Pearl Harbor, Oahu. As Japanese aircraft screamed through tropical skies, American gun crews fought back with everything available. 5-inch naval guns thundered from damaged ships, hurling shells skyward at attacking dive bombers and torpedo planes. Each shell required manual fuse setting, a sailor turning a wrench against a clockwork mechanism while enemy aircraft dove through defensive fire. Most shells exploded harmlessly in empty sky, their preset timers detonating them seconds too early or too late. Some never exploded at all. Others fell back to Earth, their contact fuses still armed. In Honolulu, 9 miles from the harbor, shells weighing 55 pounds crashed through roofs, detonated in streets, tore through buildings. The Hayasaki family died when a 5-inch shell flew through their restaurant window during breakfast service. Father Jitsuo, sons Jackie and Robert, daughter Shirley, and nephew George perished instantly along with 7 young men eating at the Cherry Blossom restaurant. 3-month-old Janet Yumiko Ott became the youngest casualty when a shell struck her home, killing her, her mother, and her aunt. By the time smoke cleared over Pearl Harbor, 68 civilians lay dead. 32 of them had been killed in Honolulu, specifically not by Japanese bombs, but by improperly fused American anti-aircraft shells landing in the city. The tragedy illustrated with brutal clarity the inadequacy of existing technology against modern aircraft. The mathematics were unforgiving. Traditional anti-aircraft fire required 3 pieces of perfect information executed in sequence under combat conditions. First, optical rangefinders had to calculate exact distance to a target moving at 300 miles per hour, potentially through smoke, clouds, or tropical sun glare. Second, height-finding equipment had to estimate altitude against fast-moving targets that could climb or dive at will. Third, fire control computers had to calculate where the aircraft would be in the 15 to 30 seconds it took a shell to reach altitude. A sailor then manually set a clockwork time fuse. The shell was loaded, the gun fired, and the fuse mechanism counted down. If all calculations were perfect, if the aircraft maintained course and speed, if the mechanical fuse functioned correctly, the shell would explode near the target. The odds of destroying an aircraft were approximately 1 in 2,500 rounds fired under ideal conditions. In combat with multiple targets maneuvering through defensive fire, the odds dropped catastrophically. The problem had existed since the First World War, but became critical as aircraft evolved. In 1918, aircraft flew at 90 miles per hour at altitudes below 15,000 feet. By 1940, modern fighters exceeded 400 miles per hour at altitudes above 30,000 feet. The gap between gunnery technology and aerial performance had widened into a chasm. The British discovered this reality facing German dive bombers over Dunkirk. Ships lacked space for additional guns. More ammunition consumed limited magazine space. Better fire control helped, but could not overcome the fundamental limitation of time fuses, requiring perfect prediction of an aircraft's future position. The Royal Navy had conducted extensive studies after the evacuation of Dunkirk in May and June 1940. Their analysis revealed disturbing truths about naval anti-aircraft capabilities. British destroyers and cruisers had expended thousands of rounds against Luftwaffe aircraft with minimal results. German Stuka dive bombers attacked with near impunity, and the mathematics explaining why were brutally simple. A Stuka diving at 250 miles per hour covered approximately 367 feet per second. The time between a shell leaving a gun barrel and reaching altitude varied from 12 to 30 seconds depending on target distance and altitude. During those critical seconds, an aircraft could change position by thousands of feet through evasive maneuvers. The gunner's calculation of where to aim became obsolete the moment the aircraft's pilot adjusted course or altitude. British ordnance experts calculated that even with perfect range-finding equipment and flawless fire control computers, the inherent unpredictability of pilot actions during combat made aerial gunnery a mathematical impossibility. The only solution was to fire such enormous volumes of shells that some percentage would, through pure statistical chance, detonate near enough to a target to cause damage. This approach consumed ammunition at unsustainable rates and still achieved disappointingly few kills. August 1940, the Department of Terrestrial Magnetism, Carnegie Institution, Washington, D.C. Dr. Merle Anthony Tuve received an impossible assignment from the National Defense Research Committee. Born in Canton, South Dakota, in 1901, educated at the University of Minnesota and Johns Hopkins, Tuve had spent his career exploring the physics of the ionosphere using radio waves. In 1925, working with Gregory Bright, he had pioneered techniques measuring the reflection of radio waves from the ionosphere to map its structure. This work laid the theoretical foundation for radar. The principle was elegant in its simplicity. Radio waves transmitted upward would reflect from the ionized layers of the upper atmosphere. By measuring the time delay between transmission and reception of the reflected signal, researchers could calculate the altitude and density of ionospheric layers with remarkable precision. When the committee approached him about developing a proximity fuse for artillery shells, he understood immediately that radio physics might provide the solution. The concept seemed straightforward. If radio waves could measure distance to the ionosphere hundreds of miles above Earth, the same principle could detect an aircraft hundreds of feet away. A miniature radio transmitter in the nose of a shell could broadcast continuously as the shell flew toward its target. Radio waves would reflect from the aircraft's metal surface. As distance decreased, the reflected signal would grow stronger, and its frequency would shift due to the Doppler effect. When the frequency shift and signal strength indicated the shell was near the target, an electronic trigger would detonate the explosive charge. The shell would become, in effect, a self-guiding weapon that could sense its proximity to enemy aircraft and explode at the optimal moment without requiring perfect aim or perfect prediction of target position. The British had shared preliminary research during the Tizard mission in late 1940. A British delegation led by physicist Henry Tizard had travelled to America carrying Britain's most sensitive military secrets, including cavity magnetron technology that revolutionized radar development. Among the information shared was preliminary work on proximity fuses. British scientists had concluded that while a proximity fuse might work in rockets or bombs, the forces involved in artillery made it impossible. A 5-inch shell experienced acceleration of 20,000 times the force of gravity when fired. No electronic device could survive such forces. Certainly not the delicate vacuum tubes that formed the only available electronic components in 1940. The physics of artillery launch were brutally unforgiving. When propellant gases ignited inside a gun barrel, pressure built to approximately 18 tons per square inch in milliseconds. This pressure accelerated a 54-pound shell from 0 to 2,500 feet per second in the fraction of a second it took to travel down the barrel's length. The acceleration forces peaked at 20,000 times normal gravity. To understand what 20,000 times gravity meant for electronic components, consider that a vacuum tube weighing 1 ounce would effectively weigh 1,250 pounds during barrel acceleration. Internal components would be subjected to forces that would shatter conventional glass, snap support wires, and tear delicate electrodes from their mounting points. Every component would need to survive these forces while maintaining precise spacing and electrical characteristics necessary for radio operation. Tuve proposed something different: a miniature radio transmitter and receiver no larger than a pint milk bottle installed in the nose of an artillery shell. The transmitter would broadcast continuously. As the shell approached a target, radio waves would reflect back. The frequency of the reflected signal would shift due to the Doppler effect. When the frequency shift reached a predetermined level indicating proximity to the target, an electronic circuit would close, sending current to a detonator that would explode the main charge. Simple in concept, impossible in execution given the technology of 1940. The project, designated Section T of the National Defense Research Committee, began on August 24, 1940 with Tuve as chairman and a handful of researchers in a laboratory at the Carnegie Institution. Their first challenge was identifying what components a working fuse required: a radio transmitter capable of operating at frequencies that would provide usable Doppler shift, a receiver sensitive enough to detect reflected signals from an aircraft several hundred feet away, an electronic amplifier to boost the received signal, a circuit to compare transmitted and received frequencies and detect Doppler shift, a power source that could provide sufficient voltage and current, a detonator triggered by the electronic circuit, safety mechanisms to prevent premature detonation. All of this had to fit inside a space approximately 8 inches long and 2 inches in diameter. Every component presented problems that seemed insurmountable. The weight budget was particularly constraining. The complete fuse assembly could weigh no more than 3 pounds. Any heavier, and the shell's aerodynamic characteristics would be compromised, affecting accuracy and range. Within that 3-pound limit, engineers had to include the transmitter, receiver, amplifier, power supply, safety mechanisms, and detonator, plus the metal housing that would protect these components during launch and flight. Every ounce mattered. Designers spent weeks debating whether to use aluminum or steel for structural components, calculating weight savings measured in fractions of an ounce. Vacuum tubes, the only electronic amplifying devices available in 1940, were fragile glass envelopes containing delicate filaments and electrodes. Standard radio tubes were 6 inches tall and weighed several ounces. The largest tubes manufactured for rugged applications were designed for mobile military radios and could withstand 10 times the force of gravity during acceleration. The fuse required tubes that could survive 20,000 times the force of gravity. At 20,000 times normal gravity, a 1-ounce tube would weigh 1,250 pounds for the fraction of a second it took the shell to travel down the barrel, forces sufficient to turn solid steel into fragments. October 1940. Laboratories across America received urgent requests from the National Defense Research Committee. Western Electric Company and Radio Corporation of America were asked to develop miniaturized vacuum tubes hardened for extreme acceleration. Sylvania developed specialized glass formulations. Raytheon experimented with tube designs featuring planar electrodes that distributed forces more evenly. Engineers discovered that conventional assembly techniques produced tubes that shattered instantly under high acceleration. The solution required innovations in every aspect of tube design and manufacturing. Glass was modified with additives that increased strength while maintaining the vacuum seal necessary for tube operation. Standard radio tube glass could not withstand the stress. Chemists experimented with dozens of formulations before discovering that small additions of specific minerals dramatically increased glass strength without compromising electrical properties. Internal components were embedded in shock-absorbing materials. Early prototypes used conventional mounting techniques where thin wires supported electrodes inside the glass envelope. Under 20,000 times gravity, these wires snapped like threads. Engineers developed new mounting systems where electrodes were bonded directly to the glass using special cements that could flex microscopically to absorb shock while maintaining electrical contact. Electrode structures were redesigned using spot welding techniques that created mechanical bonds capable of surviving extreme stress. Conventional tube electrodes consisted of thin metal sheets formed into precise shapes and held in position by support wires. The proximity fuse tubes required electrodes machined from solid metal and welded to support structures using techniques borrowed from precision watchmaking. The filaments that heated cathodes to emit electrons presented particular challenges. Standard tube filaments were coiled tungsten wire, delicate and prone to breaking under shock. Proximity fuse tubes used filaments wound with special tension patterns and supported at multiple points to prevent breakage. Some designs eliminated filaments entirely by using cold cathode emission, though this approach required higher voltages and more complex circuitry. By spring 1941, after thousands of design iterations and hundreds of thousands of dollars in development costs, acceptable tubes emerged from production lines measuring less than an inch in height and capable of surviving 20,000 times the force of gravity during acceleration. These tubes, designated specifically for proximity fuse use, represented miniaturization achievements that would not be matched in commercial electronics for another decade. The manufacturing process for these specialized tubes required precision that exceeded anything in the electronics industry. Each tube went through more than 40 individual manufacturing steps. Workers assembled components under microscopes. Quality control rejected tubes for defects invisible to the naked eye. A single speck of dust inside the glass envelope could cause electrical arcing that would destroy the tube during operation. Testing was equally rigorous. Every tube was placed in a centrifuge and spun at accelerations simulating gun launch. Tubes that survived were then operated electrically to verify proper function. Reject rates in early production runs exceeded 70%. Only through months of manufacturing refinement did production yields improve to acceptable levels. The power source presented equally daunting challenges. The fuse needed approximately 90 volts to operate the vacuum tubes and trigger circuits. Standard batteries of 1940 could not survive 20,000 times gravity acceleration. Chemical cells would rupture, spilling electrolyte. Even if the battery survived launch, it would need to function immediately upon shell firing, providing full voltage and current with no warm-up period. Harry Diamond and Wilbur Hinman at the National Bureau of Standards developed an ingenious solution: a glass tube filled with electrolyte solution sealed with metal plates at each end. When the shell was at rest, the liquid remained in the center of the tube, isolated from the metal plates. No electrical connection existed, and the battery remained dormant. When fired, centrifugal force from the shell's spin forced the electrolyte outward against small pieces of metal embedded in the tube walls. Chemical reaction between the electrolyte and metal plates generated electrical current. The battery activated only when the shell was spinning, providing a built-in safety mechanism that prevented premature detonation. The elegance of this design solved multiple problems simultaneously. The battery could not activate accidentally because it required shell spin to function. The battery had indefinite shelf life because no chemical reaction occurred until activation. The battery was inherently safe because it could not generate current until the shell was fired. Testing proved the design worked reliably, but manufacturing these batteries at scale required developing entirely new production techniques. May 6, 1941. Dahlgren Naval Proving Ground, Virginia. 6 prototype fuses built by the National Bureau of Standards team were loaded into air-dropped bombs and tested over water. Radio transmitters activated. Receivers detected reflections from the water's surface. Electronic circuits triggered detonators. All 6 bombs exploded at the correct altitude. The success validated the basic concept, but bombs experienced only a few hundred times the force of gravity during acceleration when released from aircraft. Artillery presented a challenge 2 orders of magnitude greater. The test proved that the radio proximity detection principle worked, that miniaturized electronics could function reliably, that spin-activated batteries provided adequate power. What remained unknown was whether any of these components could survive the 20,000 times gravity launch forces of naval guns. By June 1941, Section T had expanded to over 100 engineers, physicists, and ordnance specialists. A former automobile dealership in Silver Spring, Maryland, became the main laboratory, with security so tight that neighbors speculated about the mysterious activities behind blackout curtains. The cover story described research into optical instruments. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The reality was a crash program to develop a weapon that Allied military leaders believed could alter the course of the war. Workers arrived and departed through guarded gates. Windows were painted over. Employees signed secrecy agreements threatening prosecution for disclosure. Even within the laboratory, information was compartmentalized. Engineers working on transmitter circuits did not know details of receiver design. Battery specialists had no knowledge of detonator mechanisms. Only Tuve and a handful of senior scientists understood the complete system. The development process revealed a cascade of engineering challenges. The antenna had to be small enough to fit in the nose while efficient enough to transmit and receive radio signals. Engineers developed a ring antenna circling the fuse body. The transmitter circuit had to generate radio frequency signals at 70 to 90 MHz. Circuit designers created transmitter designs using just 3 vacuum tubes operating in configurations that pushed the limits of 1940s electronics theory. The receiver circuit had to detect signals 1/millionth the strength of the transmitted signal. Amplifier stages using 4 vacuum tubes provided sufficient gain. The challenge was maintaining amplification stability, while the shell spun at hundreds of revolutions per second and experienced aerodynamic forces that varied continuously during flight. Engineers developed feedback circuits that automatically compensated for these variations. The Doppler detection circuit compared transmitted and received frequencies, closing an electrical contact when the difference indicated proximity to a target. This comparison circuit had to function reliably despite temperature variations, voltage fluctuations from the battery, and electrical noise from other fuse components. The final design used thyrotron tubes, gas-filled devices that could switch high currents with precise timing. December 1941. The attack on Pearl Harbor transformed the proximity fuse project from important research to critical priority. The Navy had been skeptical that electronics could survive gun launch. Witnessing the inadequacy of time fuses during the Pearl Harbor attack eliminated all doubts. Senior naval officers who had questioned the program's feasibility now demanded accelerated development and immediate deployment. Production contracts expanded from millions to hundreds of millions of dollars. Johns Hopkins Applied Physics Laboratory was founded on March 10, 1942, to centralize development and coordinate with military services. The laboratory, established in a former garage in Silver Spring, Maryland, grew within months to employ hundreds of scientists and engineers. 5 companies received contracts to mass-produce fuses following designs developed at APL. Crosley Corporation in Cincinnati, RCA, Eastman Kodak, General Electric, and McQuay Norris committed entire factories to fuse production. Over 100 factories would ultimately participate, producing components for fuses that each contained approximately 130 miniaturized parts. The goal was 40,000 fuses per day by late 1943, 70,000 per day by war's end. Achieving these production rates required developing manufacturing techniques that did not exist. Assembly line methods used in radio production could not be directly applied because proximity fuse components required precision exceeding commercial standards. The secrecy surrounding the project was absolute. Workers assembling components never knew what the final product would do. Factory supervisors told employees they were making radio parts for military communications equipment. Different companies manufactured different subassemblies. Final assembly occurred at secure facilities, where armed guards patrolled perimeters. The designation variable time fuse was chosen specifically to mislead anyone who might learn of the project. The name suggested an advanced mechanical timer, not a radio proximity sensor. The code word POSIT was used in military communications. Even this code word was misleading, suggesting position measurement rather than proximity detection. Even after combat use began, captured fuses that failed to detonate were assumed to be some kind of advanced time fuse. Japanese and German intelligence never determined the true nature of the technology. Both Axis powers recovered unexploded shells containing proximity fuses. Japanese ordnance experts examined several fuses recovered from duds that fell in the ocean and were retrieved by divers. German engineers obtained fuses from shells that failed to detonate during the Battle of the Bulge. In both cases, examination revealed the presence of vacuum tubes and electronic components, but analysts concluded these were timing circuits of unusual sophistication. The concept that a shell could carry a functioning radio transmitter and receiver seemed beyond the technological capabilities of 1940s electronics. This failure of imagination proved to be one of the war's most effective counterintelligence successes. August 12, 1942. Chesapeake Bay, Virginia. The cruiser USS Cleveland conducted the first comprehensive test of production proximity fuses against drone aircraft. 3 radio-controlled target drones were launched to simulate aerial attack. Cleveland's 5-inch guns required fewer than 10 rounds to destroy all 3 aircraft on the first day of testing. Naval authorities cancelled the remainder of the 2-day test schedule and immediately authorized mass production and fleet deployment. The test results exceeded even optimistic predictions. In tests over the previous 2 years, time-fused shells scored hits, requiring an average of 2,500 rounds, fired per aircraft destroyed. Proximity-fused shells destroyed aircraft with dramatically fewer rounds, demonstrating 25-fold improvement in effectiveness. The implications were staggering. A ship with a limited magazine capacity of several thousand rounds could now defend against many times more aircraft than previously possible. Ammunition expenditure rates would drop dramatically, extending the time ships could remain on station without replenishment. Most importantly, ships would survive encounters that would have overwhelmed their defenses using conventional ammunition. Production accelerated through fall 1942. The first combat-ready fuses reached fleet units in October. The cruiser Helena received 500 rounds of proximity, fused 5-inch ammunition, carefully distributed to prevent accidental disclosure if the ship was damaged. Instructions emphasized that proximity fuses were to be used only over water, where duds would sink beyond enemy recovery. Gunners were trained but not told how the fuses functioned. Training officers explained only that the new ammunition would explode near targets automatically, without requiring manual fuse setting. Gun crews were instructed to treat proximity fused rounds identically to conventional ammunition in terms of loading and firing procedures. The fuses required no special handling beyond keeping them dry and avoiding electrical short circuits. Initial fleet reaction ranged from skepticism to curiosity. Gunners accustomed to time-fused ammunition doubted that any automatic system could work reliably under combat conditions. Officers worried that premature detonations might damage their own ships. Everyone questioned whether the new ammunition would prove effective against real targets under actual combat conditions, rather than carefully controlled tests. The morning of January 5, 1943, resolved all doubts. Lieutenant Cochran's salvos destroyed 1 Vals dive bomber and damaged a second. The gun crews had achieved aerial kills without perfect prediction of target position, without manual fuse setting, without the complex calculations that had limited anti-aircraft effectiveness since the technology's inception. Word spread through the fleet immediately. Ships that had received proximity fuses began using them in every engagement. Cruisers, destroyers, and battleships reported kill ratios far exceeding anything achieved with time fuses. Enemy pilots noticed something had changed, but could not understand why. American ships that had previously required hundreds of rounds to drive off attacks were now destroying aircraft with just a few salvos. By March 1943, 25% of all anti-aircraft ammunition issued to the Pacific Fleet contained proximity fuses. These rounds accounted for over 50% of all Japanese aircraft destroyed by naval gunfire. Proximity fuses proved 3 times more effective per round than conventional time fuses under identical conditions. Against fast-moving targets in night engagements, the advantage increased to 7-fold. Ships previously defended by walls of steel that relied on volume of fire could now achieve aerial kills with a fraction of the ammunition expenditure. The tactical implications transformed naval operations throughout the Pacific. Task forces could operate for extended periods without ammunition replenishment. Ships with limited anti-aircraft batteries could defend themselves effectively. Smaller vessels like destroyers and destroyer escorts achieved defensive capabilities previously possible only for cruisers and battleships. The effectiveness of proximity fuses triggered Japanese tactical changes that Allied intelligence observed but could not fully explain. Japanese aircraft began attacking from higher altitudes, sacrificing bombing accuracy to remain outside effective range. Torpedo bombers approached at wave-top altitude, where radio reflections from the ocean surface caused premature detonations, though this tactic made them vulnerable to smaller caliber automatic weapons. Dive bombers released at steeper angles to minimize exposure time to anti-aircraft fire. These adaptations reduced Japanese strike effectiveness, while failing to restore the advantage they had enjoyed earlier in the war. American ships continued to shoot down Japanese aircraft at rates that made conventional attacks unsustainable. Admiral William Halsey credited proximity fuses with fundamentally changing the balance of power in the Pacific Naval War. Japanese torpedo bombers had been particularly effective in night attacks when visual tracking was difficult and time fuses were nearly useless. With radar detection and proximity fuses, ships could engage aircraft effectively in total darkness. Radar operators would track incoming aircraft and direct gun batteries to open fire. Proximity fuses would explode automatically near targets that gunners could not even see. During 1943, despite using proximity fuses in only 25% of ammunition expended, over half of Japanese aircraft destroyed by anti-aircraft fire were killed by proximity-fused shells. The statistical analysis was unambiguous. Proximity fuses had fundamentally altered the odds of survival for both American ships and Japanese aircraft. October 1944, the Philippines. Japanese forces, facing inevitable defeat, implemented a strategy that would test American defenses to the breaking point. Special attack units, officially termed Shinpu Tokubetsu Kogeki Tai, but known universally as kamikaze, began deliberate suicide attacks against American ships. The first organized kamikaze attacks struck during the Battle of Leyte Gulf on October 25, 1944. The tactic was born from desperation and Japanese recognition that conventional attacks had become ineffective. Experienced pilots had been systematically destroyed over 2 years of attrition. Replacement pilots received minimal training, sometimes as little as 40 flight hours before being sent into combat. This was insufficient for bombing and torpedo attacks that required precision navigation, formation flying, and accurate weapons delivery. Kamikaze attacks required only enough skill to keep an aircraft pointed at a target and sufficient determination to continue through defensive fire. Japanese commanders calculated that suicide attacks would achieve higher hit ratios than conventional bombing because the entire aircraft became the weapon. A pilot who succeeded in crashing his plane into a ship was guaranteed to inflict damage, whereas conventional bombing achieved hits only occasionally even under ideal conditions. Proximity fuses proved essential against kamikaze attacks, though their effectiveness was complicated by the nature of the threat. Conventional attacks saw aircraft approach, release weapons, and attempt to escape. Proximity fuses destroyed attackers at distances where damaged aircraft would miss their targets or be forced to abort. Kamikaze attacks removed the escape phase. Pilots flying damaged aircraft continued toward targets, sometimes surviving long enough to crash into ships even after sustaining damage that would have caused conventional attackers to abort. The solution required concentration of fire that destroyed aircraft completely rather than merely damaging them. Ships increased rates of fire, created denser patterns of proximity, fused shells, and engaged targets at longer ranges. The goal was not just to damage attacking aircraft, but to destroy them so thoroughly that no portion of the aircraft could reach the ship. The destroyer USS Hadley and destroyer escort USS Evans, operating as radar pickets off Okinawa, faced 156 attacking aircraft on May 11, 1945, during a 90-minute engagement that became one of the war's most intense aerial battles. Hadley destroyed 12 aircraft before being struck by 4 kamikazes that remained airborne long enough to crash into the ship, despite being hit by anti-aircraft fire. Evans destroyed 23 aircraft before damage forced her withdrawal. Post-action analysis showed that proximity fuses had been indispensable, destroying aircraft at ranges where time fuses would have been ineffective. Without proximity fuses, both ships would certainly have been sunk in the first 30 minutes. As it was, both ships survived, though severely damaged, and their crews' actions earned them Presidential Unit citations. Statistical analysis from the Pacific War documented the effectiveness precisely. Between October 1944 and August 1945, American naval forces destroyed 278 Japanese aircraft using proximity-fused ammunition. Ralph Baldwin's analysis in his authoritative study showed that only 46 would have been destroyed using conventional time fuses under identical circumstances. The 6-to-1 effectiveness ratio translated directly to lives saved and ships kept in action. At Okinawa, where American ships faced the most intensive kamikaze operations of the war, proximity fuses accounted for a significant percentage of Japanese aircraft destroyed, though the majority of kills still came from combat air patrols and shorter-range automatic weapons like 40mm and 20mm guns. June 12, 1944, the fields of northern France. While proximity fuses revolutionized naval warfare in the Pacific, restrictions had prevented their use over land where unexploded fuses might fall into enemy hands. German technical intelligence had proven capable of reverse engineering captured equipment. The Luftwaffe had obtained examples of American and British radar systems from crashed aircraft and developed countermeasures. Allied commanders feared that German scientists might duplicate proximity fuse technology if given access to intact examples. But the V-1 flying bomb campaign against London forced reconsideration of these restrictions. Beginning June 13, 1944, just 1 week after D-Day, Germany launched thousands of V-1 cruise missiles at England with over 120 per day at the height of the assault. These weapons, essentially pilotless aircraft powered by pulse jet engines, flew at 400 miles per hour at altitudes below 2,000 feet. Traditional anti-aircraft defenses struggled against targets traveling at such speeds and altitudes. Time-fused shells were nearly useless because the V-1's low altitude and high speed meant gunners had only seconds to engage before the weapon passed overhead. Fighter aircraft could intercept Vone's second but required precise coordination and favorable positioning. Many Vone's second penetrated air defenses and struck London, causing thousands of casualties. Churchill personally authorized use of proximity fuses against Vone's second despite the risk of technology disclosure. The decision reflected the severity of the threat. If the V-1 campaign continued at peak intensity, London might become uninhabitable. The psychological impact on British civilian morale could be devastating. Any weapon that could stop the Vone second was worth the risk of technical compromise. Modified fuses were rushed into production at Crosley Corporation and flown across the Atlantic by special Lancaster bomber flights. British 3.7-inch and American 90mm anti-aircraft guns deployed along the English coast began firing proximity-fused ammunition against incoming Vone second in mid-July 1944. The effect was immediate and overwhelming. During the first week of proximity fuse use, kill rates increased from 10% to 24%. Gun batteries that had previously struggled to destroy 1 Vone-inch 10 engagements were now killing nearly 1 in 4. By the fourth week, as gunners gained experience with the new ammunition, 79% of Vone's second attempting to cross the coastal gun belt were destroyed by proximity-fused anti-aircraft fire. On August 28, 1944, toward the end of the V-1 campaign, radar detected 104 Vone second approaching England in a concentrated attack. Proximity-fused anti-aircraft guns destroyed 68 before they could reach populated areas. Of the remaining 36, fighter aircraft destroyed 32. Only 4 Vone second reached London. The British capital was saved by technology developed on the other side of the Atlantic. December 16, 1944. The Ardennes Forest, Belgium. German forces launched their final major offensive in the west, attacking through terrain considered impossible for armor. The Battle of the Bulge caught American forces by surprise in weather that grounded air support and allowed German armor to achieve initial breakthroughs. Colonel George Axelson, commander of the 406th Artillery Group at Monschau, Germany, made an unauthorized decision that day. Facing massed German infantry assault in deteriorating weather conditions, he ordered his gunners to use proximity fuses in ground combat, despite strict prohibitions against land use. The emergency, he decided, trumped the restrictions designed to protect the fuse's secrecy. 3 days later, on December 19th, as the scope of the German offensive became clear, General Dwight Eisenhower formally requested authorization to use proximity fuses in ground operations throughout the battle zone. The Supreme Allied commander argued that the tactical situation justified risking technical compromise. All restrictions were removed on December 21, 1944. The effect on German forces was catastrophic. Traditional artillery fired shells that buried themselves in mud or snow before exploding, directing energy downward and limiting fragment distribution. Much of the explosive force was wasted cratering the ground. Fragments were absorbed by soil or deflected downward harmlessly. Infantry in even shallow trenches were relatively safe from ground-burst artillery. Proximity-fused shells detonated 20 to 50 feet above ground, showering fragments over areas 50 times larger than ground-burst shells. The explosion occurred in open air, where nothing absorbed or deflected fragments. Fragments radiated outward in all directions, creating a lethal zone covering thousands of square feet. German infantry advancing through open areas found themselves subjected to air bursts that no foxhole or trench could protect against. Each shell created a lethal fragment pattern covering over 3,000 square feet compared to 60 square feet for conventional ground-burst shells. Soldiers who had survived artillery barrages throughout the war by taking cover were cut down in their foxholes by fragments that rained down from above. General George Patton, whose Third Army received priority allocation of proximity-fused ammunition, documented the devastation in reports to higher headquarters and personal correspondence. On the night of December 25th, Christmas night 1944, his artillery caught a German battalion attempting to cross the Sauer River near Echternach in Luxembourg. A single American artillery battalion firing proximity-fused shells killed 702 German soldiers by actual count conducted after the battle. Patton wrote enthusiastically to the War Department, "The new shell with the funny fuse is devastating. We caught a German battalion which was trying to get across the Sauer River with a battalion concentration and killed by actual count 702. I think that when all armies get this shell, we will have to devise some new method of warfare. I am glad that you all thought of it first." Between December 1944 and March 1945, from the Battle of the Bulge through the crossing of the Rhine River, proximity-fused artillery shells calibrated for airburst detonation took fearful tolls on German forces. Advanced fire control radar enabled artillerymen to destroy targets on reverse slopes of hills, where direct observation was impossible, and beneath forest canopy, where conventional fire achieved limited effect. Artillery forward observers who previously needed visual contact with targets could now direct fire using radar alone. Shells would explode above German positions regardless of terrain or vegetation. The psychological effect was as devastating as the physical casualties. German soldiers learned quickly that proximity-fused artillery could kill them anywhere, that no terrain feature provided protection, that the Americans possessed a weapon against which traditional infantry tactics were useless. The Germans captured approximately 20,000 proximity fuses when they overran an American ammunition dump during the initial phases of the Battle of the Bulge. This represented the intelligence windfall that Allied commanders had feared. German ordnance experts rushed captured fuses to technical intelligence facilities for detailed examination. Engineers carefully disassembled fuses, photographed components, tested vacuum tubes, and analyzed circuit designs. Reports were prepared documenting the fuse's construction and attempting to determine its operating principles. But the conclusion reached by German analysts was that the fuses could not possibly function as intended. The technical specifications seemed impossible given Germany's understanding of electronics technology. Electronics that could survive artillery launch forces were considered beyond current capability. The miniaturization required to fit functioning radio equipment into such small spaces was deemed impractical. The power requirements for a radio transmitter and receiver exceeded what any battery small enough to fit inside the fuse could provide. The Germans assumed the fuses were some kind of advanced time mechanism they did not fully understand, possibly using electronic components to achieve more precise timing than conventional clockwork mechanisms. The fuses were warehoused and eventually abandoned as German forces retreated eastward. The secret remained secure not through security measures, but through German disbelief that the technology could exist. This failure of imagination represented one of the war's most remarkable intelligence failures. German scientists and engineers possessed the theoretical knowledge to understand radio proximity detection. German radar technology was sophisticated, in some areas matching or exceeding Allied capabilities. Yet confronted with physical evidence of working proximity fuses, German analysts concluded the devices could not function as designed because their own electronics industry could not produce equivalent components. March 1945, Iwo Jima, Bonin Islands. American forces preparing to assault the heavily defended island faced concentrated anti-aircraft and shore battery positions dug into volcanic rock. Marines landing on the beaches would face devastating fire from positions that conventional bombing had proven unable to destroy. VT proximity fuses were modified for use in bombs dropped from aircraft. The fuses detonated several feet above ground, creating airbursts over enemy positions that conventional bombs could not effectively engage. B-24, Liberator bombers and Navy carrier aircraft dropped proximity, fused bombs on Japanese anti-aircraft positions and fortified bunkers before Marines landed on February 19. The results exceeded expectations. Airburst detonations caught Japanese gunners in the open and destroyed equipment that would have remained undamaged by near-miss ground bursts. Bunker entrances and gun positions excavated into hillsides were vulnerable to airbursts that directed fragments downward into positions that would have been protected from conventional explosions. The preliminary bombardment using proximity-fused bombs significantly reduced casualties during the initial landing phase. By August 1945, over 22 million proximity fuses had been manufactured at a cost exceeding $1 billion in 1940s currency, equivalent to approximately $15 billion in modern dollars. Each fuse contained 130 miniaturized electronic components, assembled with precision exceeding anything in the consumer electronics industry. The supply chain involved 87 firms using 110 factories spread across the United States. Crosley Corporation, RCA, Eastman Kodak, General Electric, and McQuay Norris served as primary assembly contractors with over 2,000 suppliers providing components ranging from vacuum tubes to battery chemicals to detonator assemblies. At peak production in early 1945, the American electronics industry manufactured 70,000 fuses daily, representing an industrial achievement as significant as the technical breakthrough that made the fuses possible. The cost per fuse dropped from $732 in 1942 to $18 by 1945 as production techniques improved and economies of scale took effect. This cost reduction made proximity fuses practical for widespread use, rather than being limited to critical situations where expense was secondary to effectiveness. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.